फॉर्मली जी स्टार्ट करने से पहले मेरी रिक्वेस्ट है सबसे कि जिन लोगों ने रजिस्टर किया है सीपीटी कोर्स के लिए काइंडली फॉर्मली स्टार्ट करने से पहले मेरी रिक्वेस्ट है सबसे कि जिन लोगों ने रजिस्टर किया है सीपीटी कोर्स के लिए काइंडली फॉर्मली स्टार्ट करने से पहले मेरी रिक्वेस्ट है सबसे कि जिन लोगों ने रजिस्टर किया है सीपीटी कोर्स के लिए काइंडली फॉर्मली स्टार्ट करने से पहले मेरी रिक्वेस्ट है सबसे कि जिन लोगों ने रजिस्टर किया है सीपीटी कोर्स के लिए जी एक एको आ रहा था फेसबुक पे लाइव किया है इस वजह से वो मैं स्विच ऑफ करना भूल गया था। तो मेरी रिक्वेस्ट है जी सबसे जिन्होंने सीपीटी कोर्स के लिए रजिस्टर किया है अपने वेब कैम तब ऑन कर लें। मैं थोड़ी देर में फॉर्मली स्टार्ट करने लगा। ये कैम मुझे ऑन नहीं है। Bismillahirrahmanirrahim. In the name of Allah, the most gracious and the most merciful. Ladies and gentlemen, Assalamu alaikum and good afternoon from Pakistan Society of Civil Engineers based in Lahore, Pakistan. A very warm welcome to all the participants who have joined us on Zoom and on Facebook. This is lecture number 47, organized under the auspices of Pakistan Society of Civil Engineers. Today's topic is structural engineering, simple facts beneath some complex phenomena. Our guest speaker today is Engineer Rizwan Mirza. Before the introduction of the speaker, it's my duty and responsibility to specify the rules of the webinar. Registered participants for CPD points have to appear live on webcam. However, there is an exception for the ladies. If they wish, they can cover their face while appearing live on webcam. During the lecture, microphone of all participants except that of the speaker shall remain in mute position. There will be a question-answer session 20 minutes at the end of the lecture. The speaker has permitted questions to be asked during the course of the lecture, slide by slide, but kindly make a note during the lecture. Questions can be asked only by typing the text in the chat box. However, you will have the privilege of asking questions through your microphone during the 20-minute question-answer session. Our participants on the Facebook do not have the facility of asking questions through their microphones. They can type the questions in the chat box, and I will read those questions, and the speaker, inshallah, will answer your questions. Now, the introduction of the guest speaker. I started 10 minutes late, I think, but still the people are coming and I have to admit them one by one. So just now the introduction of Engineer Rizwan Mirza. He is not a stranger to PSCE. He is not only among the few founder members, who was involved in the initial idea for creating this society. In fact, he is an architect of the vision and the aims for which this society has been established. He is also the editor-in-chief of the publication board of the society. I'm sorry, I have to stop. People keep on coming, those who are late, and I'm admitting them, and I would again request them, please come on time so that I don't get disturbed while making the introduction of the speaker. Rizwan got his BSc Civil Engineering degree from UET Lahore in 1980. Since then, he worked in the private sector for a few years before establishing his own consulting firm in 1987. Now, his introduction is very long, but here I cannot read all his achievements during his lifetime. So just I would be giving a very brief summary of his experience. He is actively practicing civil and structural engineering since 1981 and possessing a broad-based experience. Structural engineering experience includes analysis and design of a variety of industrial, commercial, residential, power transmission, sanitary, and prefabricated, pre-stressed concrete structures using American and other international standards. Preparation of bidding documents, technical specifications, bill of quantities, and engineers' cost estimates, undertaken bid evaluations and certifications of contractors' bills. He has also undertaken technical and financial feasibility studies, conducted arbitration proceedings, carried out site inspections, and evaluated safety of existing structures. He is proficient in computer-aided analysis and design, has developed a variety of technical softwares. He has also worked on overseas projects, and work has been internationally reviewed. He is proficient in written and spoken English, experienced in report writing and other business communication. His affiliations are with Pakistan Engineering Council, Institution of Engineers Pakistan. He is the founder member of Pakistan Society for Earthquake Engineering and the founder member of Pakistan Society of Civil Engineers. He is the co-author of publication. Mirza Rizwan Durrani, The Role of Analytical Tools in Evaluating Damaged Concrete Structures. And with Noor Durrani Sahab, Rizwan is a co-author of Legal and Technical Aspects of Earthquake-Induced Failures in Pakistan. He has a teaching experience too. He has offered undergrad courses at National College of Arts in Lahore, have lectured in various seminars and workshops, and he has been a paper setter and examiner for undergraduate and technical diploma courses in civil engineering. So a very brief introduction of Rizwan Mirza. I'm sorry, I have been a bit messy while introducing Rizwan. Still, a lot of people are coming late, and I get disturbed by when the screen just becomes blank when I start. It is disturbing my flow while I'm introducing the speaker. So kindly try to come on time next time. Thank you. Rizwan, the floor is yours. Please continue.
Thank you. Can you see the screen?
Gigi is okay. Please go ahead.
Okay. I have very little time at my disposal. So without much ado, I'll start right away with what I have to present today. My presentation um, comprises some cherry picking that I have made uh, from amongst the various aspects of structural engineering that are experienced by anybody who's in practice. I've tried to divide my presentation into three broad sections. One comprises structural systems. This is a separate heading so that we can view the major structural systems as a whole and try to uh, classify them on a rational basis. Second part comprises individual topics, but I think interesting topics that are encountered in analysis and design of various types of structures. And the third part, again, equally substantial in its length, comprises the seismic forces. I have included seismic forces because the area of seismic forces is rather hazy for most of the people. So I have tried to approach the apparently difficult subject with an attempt to simplify what underlies an apparent complexity. So my first topic is structural systems. As we all know, we are aware of beams, trusses, arches, suspension cables, and compression members and straight cables, but we don't tend to find any unifying lines between these structural systems. We study them one by one and one at a time, and forgetting that there is a common thread that connects all of them. So my attempt today would be to find that common thread. Let's look at beams. Beams, assuming a simple beam having two supports under a uniform load, would have a bending moment which is equal to WL square divided by 8 at the middle. This is resisted by tension at the bottom and compression at the top. As you would note on the right-hand sketch, the blue part that I have removed and put at the top is not being utilized fully. As the strain diagram and stress diagram show, this area is under very low stress. This is a problem that is associated with the phenomenon of bending. So you will often see that in reinforced concrete and sometimes in reinforced concrete, and more often than not in steel structures, we have rather long webs and thick and wide flanges at the top and at the bottom. This is an effort to place the material farthest away from the neutral axis so that it is most effectively utilized. Now let's move to the left. Look at the truss, which is under a similar condition. Truss is also subjected to the same load W, having the same span L, and it also has a more bending moment equals to WL square by 8. It resists the same bending moment by tension at the top and compression at tension at the bottom and compression at the top. But this time, a large amount of material has been removed from the web. As you would see, the top chord is a member comprising angular sections. Bottom chord is a member comprising angular sections, while the web is again a crisscross of members comprising angular sections, some in tension, some in compression. So essentially, this is identical behavior to that of the beam, where the web is resisting the shear, top part is resisting the compression, and the bottom part is resisting the tension. Let's move to the next slide. Let's look at the arches. Arches are again subjected to the same bending moment, having the same span L and subjected to the same load W. The bending moment would be WL squared by 8. But what differentiates the arches from the beams is its curvature. But the curvature alone is not enough to differentiate the arch in its behavior from that of a beam, because in order to resist the bending, it will have to develop compression at the top and tension at the bottom, so that we cannot get rid of the inefficient phenomenon of bending. It acts like an arch, not because of its shape, but because of its shape and the ability of the two supports to resist the horizontal sliding movement. The force H is that you see at the bottom. At the left, the force is facing rightwards. At the right, the force is facing leftwards. So as the arch tries to move outwards at the two supports, these two supports resist the movement. As a result, at every section, the equation of bending moment includes these horizontal components of reaction, which are H. At the midspan, the bending moment is WL squared by 8 minus H into rise. If the shape of the arch is that of a parabola and the load is uniformly distributed load, bending moment will become 0. If the shape is not that of a parabola, while the load is that which is close to a uniformly distributed load, there will be some relief in the bending moment, but there will be a bending moment. So for an ideal arch, it has to be given the shape, the geometry of the bending moment diagram for which it is supposed to resist. For a point load, it has to be a triangular arch. On the left, you see the human foot, which is an arch. And this arch has two components. The red component is the arch in the longitudinal direction, and the right component, blue in direction, is the transverse arch. You walk on 2 feet because you are able to resist a couple shown in red arrows because of these two arches. And this was the development that distinguished Homo erectus, the first amongst the species of Homo sapiens, which could walk on 2 legs rather than in a crawling fashion. So this arch is very spectacular example of what arches can achieve without much of reinforcement. This is in China, considered to be the longest masonry arch, 479 feet long. The the span to depth ratio, 106 feet is the depth, is 4.5. If the span to depth ratio were small, the force at the springing of the arch would be very large. So in order to reduce the force at the springing, which is the bottom support, the span to depth ratio has been kept very large. It has a width of 4 lanes, which is 81 feet for this bridge. So the thickness of the arch is 8 feet at the crown. It was completed in 2001. This is in stone masonry. Let's go to the next slide and see what happens when we reverse the arch. Kindly try to retain the images of the earlier slides as we move to the next, because of the fact that all these structural systems have a common thread, which I'm continuously pointing out to, which is a span L and a bending moment WL squared by 8. This suspension bridge again is having a span L and has to resist the bending moment WL squared by 8. But as we know, it cannot, because it comprises a cable. So what happens is that as the arch developed a resistance H at the springing, the bridge develops a tension T at the top, which multiplied by the dip of the bridge. As we talked about the rise of the arch, in the case of the bridge, we will talk about the dip of the bridge. The distance, vertical distance from the height of the tower to the deck would be the dip. So horizontal force multiplied by the dip would be subtracted from the equation of the bending moment. So bending moment will be that in the equivalent simply supported beam minus T into the dip will be 0. In this case, it will be 0. Whether you predetermine a shape of the suspension cable or you don't, because you cannot predetermine the shape of the cable. It will assume the shape of the cable according to the type of load that it is subjected to. If you have ever seen a cable in the circus, when one person moves over the cable assumes a V-shaped configuration. When two persons move over the cable assumes a shape having a horizontal line and 2 inclined lines. In this case, you can't afford to have the bridge moving continuously in the vertical direction. So there is a stiffening mechanism at the bottom. The deck is supported by a stiffening member, which is not the beam resisting the bending moment that is being resisted by the bridge itself. It's a localized stiffening member which removes that movement as the load moves along the span. The up and down movement as you move along the bridge will not take place if the stiffening truss has been adequately designed. This is an interesting aspect of the suspension bridge, and it shows you how efficient these bridges are. The bridge at the bottom is comprising, it comprises natural materials. The rope that has been used is natural fiber. This bridge, which is 108 feet long, it is in Peru, the South American state, and the people of this civilization have been living here for 600 years, and they every year they remove this bridge and they reconstruct it, and it has never had a reported failure. It's just 4 feet wide. It's used for walking, and women weave the rope and men construct this bridge. This is just an example of how efficient. You can't have a rigid bridge over 108 feet long span. Now come to compression members. They pose their own difficulties, and this is a class in their own. I will not talk about compression members because there is no such thing as compression members. I will talk about beam columns, because pure columns would seldom exist and pure beams will seldom exist. Even in frames, the beams are carrying some tension or some compression, and even in columns, there is some inherent crookedness or inherent eccentricity, or that imposed by the connecting members, and the structure undergoes some bending. So the diagram that has been drawn at the right shows a diminishing amount of eccentricity as you move from the right to the left. The eccentricity is decreasing, or in the reverse direction, from upwards to downwards in the right direction, the eccentricity is increasing till such time that at the bottom it's a pure beam, and at the extreme left it becomes a pure column, which are both notional concepts, not concepts in reality. Leonhard Euler was the first person who identified the difficulty associated with columns. My teacher who taught me this concept is sitting, I have the honor that he's sitting here. This is a great honor for me. I learned this formula, this relationship from him. And this clearly states that the buckling load that can be carried by the column is pi square is into modulus of elasticity of the material into moment of inertia of the material divided by L square. I would draw your attention to one fact. That fact is very interesting. This has two stiffness coefficients, but it does not have any strength coefficient. There is E, which is related to the material, and there is I and L, which are related to the section. So regardless of the strength, the answer that you get would be the same, which means that Euler's buckling takes place depending only on the E, I, and L square of the column and not on the strength itself. So R is I over A under root, and I is A into R square. What is R? Again, it's a notional value, but as we know that I is equal to A R square is a famous relationship. You can conceive R as a circle at which material can be considered to be concentrated. So area concentrated at a distance R would provide you a moment of inertia I. So area into R square will be the moment of inertia by definition. This is just a easy way to understand physically what has been derived from rigorous mathematics. So F critical, the critical stress would be pi square E over L over R square. In the right drawing, this has just been plotted. The top drawing, which is drawn in blue, shows that as the L over R ratio decreases, the allowable stress is increased. It would have increased indefinitely had I not capped it at the allowable stress value, because beyond that, the material would have crushed in any case. So the cap that you see, the horizontal line that you see, would not be there in the Euler's formula. It has been placed in order to cut away the line of the horizontal, in order to stop the line of the Euler's formula, so that we cannot utilize the Euler formula beyond the crushing strength of the material. Bottom is the approach of American Institute of Steel Construction, which says that you don't just stop it randomly at the crushing strength, but have a curve between the Euler's formula and the location where you would stop for the limitation imposed by the crushing strength. There are two graphs drawn here. One is for A36 material and one is for A50 material. You would see that beyond the Euler's, beyond the point where Euler's formula starts governing, the two lines are different. The one which has higher strength would deviate from the other. When the KL over R becomes larger, regardless of the strength, both lines become the same, because they have nothing to do with the strength when you cross a higher value. It's like something like 100 or 120 L over R. It's just a ratio. Compression members are, if you follow the nature, look at the sugar cane stem, it is hollow and it has septums. Look at the avian wing bone, which is cellular in section, and it has a crisscross of septums. So nature teaches us that compression members need to have large moment of inertia, and they need to increase their R value. The rightmost diagram that has been drawn for illustration purposes shows that we can achieve a very large value of moment of radius of gyration with the same area, utilizing the same area. Those who are not currently in the practice of design should know that we cannot indefinitely thin out the member by being carried away and indefinitely or recklessly increasing the diameter while thinning out the wall thickness, because that would result in web crippling. Think of this can which you get for the drinks, and if you compress that can, the walls which are very thin would buckle, although they have a lot of moment of inertia, but there will be web crippling as a result. So D over T value around D 12 or 10 or even slightly larger would sound good, but D over T of say 20 would be very dangerous. Probably it's not permitted. So there's a limit to what you can achieve. At the left bottom, you can see the assortment of what is commercially available in the steel structure sections which are used in compression. This is a steel concrete member subjected to bending and axial tension, and you will treat bending and axial tension as pairs, and you enter the diagram In the vertical axis, you touch the diagram at the load which you need to carry, go horizontally, touch the diagram of the interaction diagram, move downwards, and this is the load that is permitted. This is the bending moment that is permitted as a maximum to be applied to the member. This interaction diagram represents a particular geometry, particular concrete strength, particular steel strength, and particular amount and arrangement of reinforcement. Generally, the books available would have 8 diagrams for 1%, 2%, up to 8% amount of steel, and then for various families of diagrams for various arrangements of steels. And you will have, on the basis of those non-dimensional diagrams, the facility of computing or estimating the required amount of steel very speedily. In the modern days, probably people would prefer to use digital computation, whereby they can come up with the amount of reinforcement. But I would strongly recommend that even if you are using digital computation, you keep a look, keep an eye where your point of P and M is located within the diagram. It's very important. A blind OK signal from the software could be very misleading. The balanced point is blue dot, where the curvature changes. E is equal to E balanced. Anything below this is tension controlled. The failure would be initiated by yielding of steel. And above that, the failure will be initiated by the compression strain 0.003 of the steel. The top part basically relates to lower story columns in a multi-storied building. The bottom part would relate to the top storied columns in a multi-storied building, subjected to large, so small amount of axial loads and large amounts of moments, while those at the top would be subjected to high amounts of axial load and low amount of bending moments, or at worst the same amount of bending moment. So the level of margin that you have, the kind of failure that you should expect, needs to be looked at by examining the position of your pair, load pair within the diagram. Tension members, as you see at the right, this is a cable stayed bridge, again are very efficient, same as the suspension bridges. Load divided by allowable stress would be the area required. The nest of the weaver bird is at the left is a tensile structure. It's hanging with the stem of a tree, and it comprises a large number of grass pieces, and it's enough for the load that it is designed to carry. So again, even nature teaches us how to carry tensile forces by weaving from the available material provided by the nature. Now let's go to design and analysis. I have to be quick. The stresses that we are dealing with, Galilei was a towering personality who was born in 1564 and who died in 1662. The importance of 1662 is that this is the same century, same year in which Isaac Newton was born. And the importance of Galileo is that he was the one who verified the Copernicus theory that the Earth is the system is heliocentric and not geocentric, unlike what the church caused man to believe. And this is the basic contribution, but he made many other contributions to physics, as we will later know in the topics that we are going to follow. His contribution, he was really a giant. This is the same period as that of Shah Jahan, who reigned in 1628 and 58. I need not say more what was taking place in our part of the world during that period. The concept of stress conformation is that when you have a state of stress at a particular plane, you can imagine other planes at which there will be other states of stress, in simple terms. So my objective today is to keep things simpler and try to identify simple concepts lying beneath apparently complex statements. As you cut the planes, various planes, from a piece having a state of stress, even that piece is a beam, notional planes, vertical, then inclined at 45 degrees, and then purely horizontal, you will see various states of stress. This is the miraculous way at which by which the state of stress is determined by the construction or by the analytical treatment of a mathematical concept which is called Moore's circle. It's very simple. Each point on the circle comprises a pair. Pair is normal stress and shear stress. You draw on the horizontal axis the normal stress on one plane, and on the same set of axes, you draw the normal stress and the shear stress on any plane at right angles to it. Join these 2 points and you hit the horizontal axis at the center of the circle. Now draw a circle from here, and what you see is the Moore circle. The radius is given at the top, center is given again at the left top, sigma vertical plus sigma horizontal divided by 2, and radius is by trigonometry, very simple trigonometry. It's apparent from what you see at the diagram below. And when you cut various circles, the forces can be computed from one more circle that you have drawn. Look at this beam. This beam has a diagonal crack, which is known as shear crack. But those who are not in design offices, for them particularly, the transformed state of stress tells us that although the stress at the vertical planes is vertical, but other planes at other than vertical orientation have other states of stress, and the red arrow shows the tensile stress, which results in the crack that is noticed in the beam, and it is labeled as shear crack, while it is a diagonal tension crack. Similarly, in this earthquake 2005 earthquake in Azad Kashmir, you will note that a similar diagonal tension crack has appeared in the wall, and it is explained by the earthquake force that has caused shear and that has resulted in a diagonal tension. Uh, Before I move forward, without taking a lot of your time, I'll just mention that this Moore circle is such a powerful concept. Excuse me, that this is extended even to sectional properties of materials. As you already know, you must have been taught during your undergrad studies that the bending theory is applicable only to the principal axis of members and not to axes other than the principal axis. These are the axes which are either the maximum or the minimum value axis. Axis of symmetry are always axis, principal axis, but not all axis, principal axes are axis of symmetry. This construction where horizontal axis represents the moment of inertia and vertical axis represents the product of inertia is used to draw a pair first and then draw the next pair. Secondly, join the two lines, find the center, draw a circle, and then compute the maximum moment of inertia and the minimum moment of inertia. And this is again the same tool that was used in determination of the stresses at various planes. So it's a very powerful sort of mathematical device which may be employed with a great degree of facility. And I assure all of you that you have studied things much more complex than this. Just have a careful look at the construction. The construction is very simple. It doesn't need anything other than high school mathematics. But it takes you very far when you wish to understand various phenomena that we encounter. Okay, let's move forward and see what kind of simplifications we make while we work. The stress strain diagram of a ductile material is at the top left. The stress goes in a linear fashion, in a hooky fashion, moves slightly to the right, about 10 times to the right, and then it goes up and up and up and up in a dotted line, and then it is extreme top where the failure takes place. But in our schools, in our lab reports, what you see is not that dotted line. What you see is the firm line, which is below the dotted line. The reason behind this is that the area that is used for the computation of the forces is not the actual area at the time that the stress is computed. It's the area that was once assumed at the start of the test, and the same area is continuously being used for computation of stress. So at every time, the area has actually been reduced, but you are using a large area. So when you use a large area, you get a reduced stress. So the error is there. So the stress fall is visible in the apparent diagram. So it's ridiculous that a material in a tensile test has withstood a very large value of stress, but has actually failed in a tensile manner at a lower value of stress. Naturally, it is ridiculous. But this is the result of a simplified assumption that the code allows you to make, which is that you can use the original area at the start of the test for computation of the stresses, which is an ease by which you don't have to stop every now and then in order to compute the diameter and then note it down and then resume the stress. At our universities and testing agencies, it has become a habit now to report using nominal area, using actual area, which is very confusing. At the end, they report two stresses. Again, using nominal area, using actual area. Some labs are doing it, some labs are not doing it. I probably would stress, it's an academic thing, nothing against or for anybody, that we should follow the standard. As the standard prescribes, we should follow it. Now let's go to the diagram to the left and see the behavior, the same behavior that we have noticed above. But for all practical purposes, for design and analysis, the curved parts are ignored. The red part that I have drawn shows you the ideally elastic, perfectly plastic behavior of the ductile materials. Material is first assumed to be ideally elastic, a perfect straight line, and then the horizontal part is the perfect straight line. The diagram at the extreme right is the same diagram as at the left, but it has been, at the center is the same diagram as the extreme left, but it has blown about 10 times. The diagram at the extreme right shows you the values of the strain at which the concrete fails, and you will note that all concretes do not fail at the same strain. But in order to keep our lives simple and in order to keep our day-to-day computation simpler, we assume the value of 0.003 as the line at which the concrete fails. Just as we have kept the horizontal line as the cut-off line and don't follow the upward curvature of the ductile material stress strain line in order to keep our lives simple, our day-to-day computation simple. Look at the witness block, which again is an attempt to keep our lives simpler. 0.85 f sub c prime is the average value, and the depth of the block is beta 1 into the depth of the neutral axis, which is reasonably simple, and it greatly simplifies your work. If somebody were to follow the stress-strain relationship represented by the right diagram, stress would need to be computed depending upon the strain. And the stress that you note in the central diagram is the strain computed by a linear stress is computed by the linear strain stress relationship, which results in a curve would not lend itself to a very easy analysis. Even in the European codes, those who adopt this so-called exact shape have to resort to many simplifications. So the simplification that has been made at the right is very simple and very reasonable. Now let's go to a very interesting topic, which is risk and safety. In our, if anybody has a question, I'm moving fast because a lot of time was wasted at the start, and I have my lectures maybe 2 years apart. And when I meet you after such a long time, I wish to say as much as I can. And I am 65 years old now. I don't know how many lectures can I give you after this one. So I try to share whatever I can. If anybody has any question, you can stop me whenever you want. Look at this diagram, which tells you the types of risks. The child at the doctor's clinic is having an injection. There could be erection and she could be injured, or God forbid, worst can happen. Look at the roadside accident that has taken place. Look at the helicopter crash. Look at the gentleman who has fallen from the stair. Look at the boy who's delivering food. They're all exposed. exposed to risk. We don't stop, taking a ride on a helicopter or, doing any of these things because they are risky. We don't. So contrast this with this. To whom it may concern, I do hereby certify that the building ABC designed by me is structurally safe and fit for human occupancy. Consulting engineer is duly signed and stamped. Is it compatible with this? The answer is no. If the society accepts this, this is not to be expected from a structural engineer. He is not to play Jesus Christ. He is a human. He cannot understand what will be the level of safety at which you can say that the building will be safe. I will see how we can approach safety. This is not, in fact, only in Pakistan or in countries like Pakistan, such certificates are demanded from institutions like Lahore Development Authority or DHAs or, Capital Development Authority. Look at how nature works. The loads and the capacities are scattered around the mean, just as human intelligence is scattered around the mean. If you have good quality control, a large number of samples are within the central part, which is the mu part, which is the mean of the sample, and extremely high value or extremely low value are fewer. The standard deviation, which is the value itself minus the average value, this number squared, sigma of this divided by the number of readings that you have taken, number of samples that have you taken, and square root of this would be the standard deviation. Standard deviation, larger the standard deviation, greater the scatter around the mean. Standard deviation has the same units as that of the quantity that you are measuring. For instance, if you are measuring the strength of concrete samples, it would not be very unusual to expect a standard deviation of something like 500 psi, which is commonly accepted as a usual sort of standard deviation for expected from concrete. But lower the standard deviation, the tighter the control. Similarly, the loads also tend to scatter around the mean. In our homes, sometimes everybody is away and there is just one person, or the home is locked. There's nobody there, and the loading is minimal, reduced to dead load. Sometimes we have parties, sometimes we have gatherings, sometimes we have religious occasions or other occasions on which the loading is very high. And similarly, in public gathering facilities, there are very large gatherings, theatrical facilities, cinema halls, and sometimes very thin, attendance. So the load varies around them. With this having in mind, let's go to the next diagram. I'm trying to make it as simple for you as possible. Try to understand it. If load shrinks, load increases in its value, the probability is very low beyond a certain value. And if the capacity reduces to a value below this value, although the probability is low, there will be failure. So, anybody who signs a certificate that I certify that the structure is safe for human occupancy is signing an incorrect certificate, because this interface between the maximum load exceeding the minimum sort of left tail of the capacity diagram shows that as the two diagrams are asymptotic, they meet the horizontal axis at the value of infinity, they are never zero. And no matter what you do, the probability of failure is never zero. You can have very large value of capacity. The probability of failure would be reduced. But still, theoretically, as the diagram is asymptotic, it will not become zero. Now, there is another type of danger, which is natural hazard danger, which is wind or earthquake, and the distribution population density of this is not having the shape that we have already seen. That was closer to the mean, higher the probability. In this case, lower the intensity, higher the probability. Small breeze, low ground vibrations are seen every day, while very large earthquakes and very severe winds are seen after so many years. So this is different in its concept. Another very important concept while discussing safety and risk is that you don't combine possibilities which are unlikely to occur together. For example, dead and live load are combined together. Dead, live, and earthquake loads are combined together. Dead, live, and wind loads are combined together. But dead, live, earthquake, and wind are not combined together, which means that we don't expect worst of earthquake and worst of wind to come together. We don't combine worst of wind and worst of snow to come together. Why? Just look at a small equation. If the probability of a statistically independent event probability of occurrence is P1, and the probability of another statistically independent event is P2, the probability of joint occurrence is P1 multiplied by P2. For instance, if P1 is 1 in 100, P2 is 1 in 100, P1 and P2 occurring jointly is 10,000. 1 in 10,000. The probability becomes so low that we disregard it. That's it. Now look at another concept, another stray concept, whether to have continuous spans or to discontinue them. You will see both types of decisions taken in buildings, in bridges, mostly in bridges. In Pakistan, you will note that many British time bridges are simply spotted. You reduce your bending moments while you have continuous bridges. You reduce your deflections when you have continuous bridges. You appear to have so many advantages. You, if you have arched bridges, the arches mutually resist the thrust of the adjoining arches, and this is a major advantage when the arches are continuous. But these are the upside of the continuity. The downside is that in continuity, if one support settles, the bending moment diagram of the adjoining or the spans next to the adjoining would change, and a failure may take place. Secondly, second part is that unless you have designed for it, continuous spans are sensitive to pattern looping, which means that the dead load is placed there at every span. We know that. But when dead load, live load is placed at one span and not at the other, or at two spans and then not at the other, the bending moment diagram changes. So one needs to be mindful of the fact what changes will be there when you have continuity and when you don't have continuity. Approximate analysis is a technique to which you must be introduced if you have before you a multi-story building and you need to quickly estimate the bending moments at the bottom. Just roughly compute the lateral shear of the earthquake force divided by the number of columns. Just brief differences that the external columns are taken as half and the internal columns are taken as one. And per column force multiplied by height divided by 2 will be the bending moment in the column. This can be done in 10 minutes, while even if you have computer facility and you intend to carry out a sophisticated analysis, even trials are not possible that fast. You must have some prior estimates of the forces before you can start undertaking the trials. Bearing pressures is my next topic. The bearing pressures are dispersed through a diagram, the equation of which was presented by Bosniak, and the charts are very famous. The chart that you see at the right is Bosniak's equation. As you move downwards and as you move rightwards and leftwards, the pressures are reducing. The contact pressure Q at the bottom of the foundation is not the same as you move downwards. It is continuously being reduced. At about 0.6 of the width of the foundation, it's almost gone. It may be something like 7% or 0.05%. So the simplification that is often made when you are in a hurry and you don't have this diagram before you is that you take 2 vertical to 1 horizontal dispersion. If you move downwards by 2 numbers, you move horizontally by 1 number, and in this fashion, you increase your footprint in both directions. Don't forget, in X direction and in Y direction, which means as you look at the plan in the length direction and in the B direction, you increase your footprint. You move by Z below the start of the foundation, Z by 2 on one side, Z by 2 on the other. So Z on the 2 sides put together, plus the original dimension B. Again, Z by 2 on one side and Z by 2 on the other, plus L in the other direction, which is equal to L plus Z. So it will be Z plus L multiplied by B plus L, the footprint at a depth of L. This will be a very large footprint. So greatly reduced contact pressure. This is one point that I wish to make. Subgrade modulus is another property of the soil that is required by structural designers very often, which is the pressure required for unit displacement. This is often expected from geotechnical engineers, that they provide you with a value of the subgrade modulus. My humble submission today is that subgrade modulus is not a property of the soil alone, because if you look at the 3 or 4 diagrams that I have drawn at the bottom, sketches, if you have a very large foundation, say 300 feet wide, a mat, and then a smaller foundation, and then still a smaller foundation, and then a very small foundation, the depth up to which the pressures go would greatly vary. And as you know, the settlements that you get are not a result of the actual compression of the material of the soil, but a reduction in the gaps are oozing out of the water. It's not compression of the clay particles or the sand particles that results in the in the settlements. So the stresses are the primary parameter that cause settlements. So the deeper are the stresses, deeper is the influence of stresses, unless it's rock, which is, which would not move, whether the stress is 1 ton or 2 tons or 10 ton per square foot. If the influence zone is large, generally you will get larger settlements. So for a mat, for the same pressure, you might get a double or triple or 4 times the settlement. So that will become the basis of your modulus of subgrade reaction. For a 10 by 10 foot foundation, the settlement may be much lower. So you will get a much higher modulus of subgrade reaction. In order to really understand what I'm saying, look at the computation that I have made at the right. Suppose the weight of a lady is 170 pounds and the weight of the shoe, contact shoe is diameter is half an inch. The area is about 0.2 inches square. The pressure under each foot when it is divided onto feet is 62 kip per square foot, about 32 ton per square foot. Look at it. Look at the number. And nothing happens. This is an interesting thing that I leave you with. Such large numbers are present around us, and they don't create an havoc because the stresses are confined to very, very low depths, and maybe the stress, generated by the human foot in this manner is confined to 1 stone depth alone. So nothing is going to happen to that stone under this kind of a stress. Support fixity is my next topic. Many people ask whether the support is supposed to be fixed or it is supposed to be taken as pinned. Look at the support when you subject the support to rotation and plus some sort of flexure bending moment. There is a tendency to have larger bending moments, larger pressures at the right and smaller pressures at the left. And as a result, there will be larger compression or settlement at the right and smaller compression or settlement at the left. And it's very difficult in geotechnical engineering to compute what kind of a rotation will take place because the standard procedures that we have are tailored for uniform settlement. So the simple technique that has been proposed is that you assume Q maximum throughout the foundation as the first assumption, compute the settlement, delta 1. Then you assume Q minimum throughout the foundation, throughout the foundation, and compute settlement 2. And then Q1 minus Q2 divided by L, tan inverse of this would be your rotation angle. This is a rough indication of what you see. If this value is large, it means when the foundation is subjected to a very large value of moment, be prepared for a large value of theta. It means large value of the structure above. In any case, I'll move fast forward from here. Even if you have exact analysis of bending moments with pinned support at the bottom and fixed support at the top, my analysis says that even if when the stiffness of the beams is taken as equal to stiffness of the columns, which is almost impossible, the difference in the answers will be only up to 12%. So in reality, it hardly matters whether you assume pinned support or fixed supports. An American Concrete Institute allows you to use subframes for your analysis. Fixed at the top, fixed at the bottom. Again, fixity at the bottom is allowed even by ACI. Lastly, if you have rigid connection, which means connections have the ability to rigidly, transfer the loads, you will assume fixed supports. When you have rigid connections, but the foundations are flexible, they have a tendency to rotate, you have to assume pinned supports. When you have hinged connections, you will have pinned supports. See the diagram at the right. The diagram at the top has very small distance between the bolts. It will not provide any significant moment transfer between the plate and the pedestal below. While the diagram at the bottom has very large distance between the bolt lines, and it's clear that the designer has the intention of transferring a significant of moment to the plates below. This is about pattern loading, and I will try to neglect it because I'm running out of time. Okay, this is a very interesting topic. I don't want to leave without this. You must have studied simple harmonic motion. Again, this was observed by Galileo when he had been imprisoned by the church. He was subject to house arrest, and the property of each pendulum to move to a certain extent and then come back, the duration that it takes, the time period is the same for each pendulum. The frequency, which is 1 over T, is equal to K over M under root. K is the stiffness of the vertical part of the pendulum, and M is the mass attached at the bottom. When you draw it in a circular fashion as a simple harmonic motion, what you get is sine curve. The diagram at the top left is a diagram which shows that no energy is being lost. The diagram below shows that the energy is being lost. The diagram at the right bottom shows the various points are sine. Let's see one point, no motion. Point 2, there is a movement at the right. Point 3, again mean position. Point 4, opposite, extreme opposite direction. Point 5, again at the mean position. So the building or the object moves, or the pendulum moves from one extreme position to the other extreme position, passing from the mean position at the points 1, 3, and 5. This is the famous circle, which shows that the cosine of the value is horizontal value, and the sine is the vertical value. So we say that displacement is sine, because the movement away from the mean of the horizontal line is a sine omega t plus phi. Phi, you neglect phi. Phi is a useless complication. Phi is the phase shift. This means that if it had already moved by an angle, just add it. For the moment that it has not already moved by any angle, you assume that phi is 0. So you take sine theta, omega a sine theta, that is equal to the vertical displacement, and the velocity would be equal to first derivative of the displacement, which will be omega a into cos theta. and the acceleration would be the second derivative of the velocity. That will be minus omega square a sine theta, or minus omega square x theta. Yeah, these diagrams right at the right show a phasal shift, that when the velocity is at its maximum, the acceleration is not at its maximum, and in fact there is a phase difference of 90 degree between velocity and displacement, and between acceleration and displacement. This is a simple explanation of what happens when a sinusoidal wave travels. When a system is damped, it means it loses energy as it moves. The waveform decreases in its amplitude, right? The model that you see of a damped system is in the middle top, which is comprising a spring, which is the stiffness of the member, m, which is the mass of the member, c is the coefficient of a viscous damper, and the equation that you set up is formulated by the facts that the force applied by the mass is dependent on acceleration. Force dependent generated by the spring is dependent on the displacement, and force exerted by the viscous damper is dependent on the velocity. So m into a, that is force into acceleration, plus c into velocity, that is c into velocity, plus k into a displacement, which spring is always exerting a force which is proportional to displacement. K is the constant that represents the stiffness of the spring. C is the constant that represents the similar, constant for the viscous damper. And you add them up and this becomes zero for equilibrium. This becomes an equation which, when solved, leads to m into lambda squared plus c into lambda plus k is equal to 0. Lambda is plugged in value, which is equal to x is equal to E, which is Euler's number, raised to the power lambda into t. T is the time. So lambda is identified by minus c plus minus the famous solution for quadratic equation. The key for you is that when the member is referred to be damped, the reference is to critical damping. Critical damping would take place when C minus 4mk is 0. This is the definition of critical damping. When C square minus 4mk is less than 0, it is called underdamped. When it is greater than 0, it is called overdamped. The lines that you see at the right, the blue line is underdamped, red line is critically damped, and black line is overdamped. So in practice, you will hear people talking about 2% critical damping, 5% critical damping. That depends how fast, with what speed the integrity of the structure is gone, or the degradation of the sectional properties takes place. So the loss of energy that comes in is returned. This is the property of each material, which represents the ability, this value, which is Z, this How much time we have left? Okay, 2-3 minutes more. You should note that seismic wave is a very complex thing. The bottom diagram shows the typical recording of a seismic wave, and it comprises so many you know components that it's difficult to apply sinusoidal equation law. There is a procedure by which you can break down such a complex wave through an infinite series into infinite number of sinusoidal waves, an example of which has been produced above in a very simplified manner. It's a digital procedure, and you pick up those waves which have significant amplitude. Those are the waves that are the major contributors to the energy of the earthquake. And the breakdown into waves of certain frequencies and amplitudes is of vital interest. If you have time, I will stop at one thing that, unless we have no questions, then I will go on and utilize the next few minutes. When you have any question?
I think, Rizwan, you first finish your lecture, then there are 2 questions on Facebook that I will read out once you finish.
Okay. Okay. The simple concept is that there is, say, a 30-second record with you of generated by an earthquake of waveform at a particular location. Note that the waveform generated at another location will be very different. Very, very different. So you cannot say that this was a signature waveform for that particular earthquake. So you take a pendulum having a mass m and 2% damping, 2% critical damping, and period is 2.5 seconds. And then you take the same pendulum, elongate the length, you get a higher period of 1 second. You take the same, object, you elongate the length further, and this period now becomes larger, now to 2 seconds. Now see what happens to this pendulum when the entire waveform is experienced by these 3 pendulums having different fundamental frequency of vibration, or having 3 different time periods. Look at the equation at the left. Omega is equal to k over m under root, t is equal to 1 over omega is equal to m over k, t square is equal to m over k, k is equal to m over r square, force is equal to m into k, m into a. This is the Newtonian law. At the end of the day, force is equal to mass into acceleration. A is force into k. So when the acceleration is experienced by a pendulum, the acceleration multiplied by the mass will become the force. And force multiplied by k will be the displacement, because k displacement by k by definition is the force required for unit displacement. So you draw the displacement diagram at the right for each pendulum, and then in the blue graph at the right, you draw what will become the behavior of various pendulums of various time periods when subjected to the same acceleration display acceleration time graph that you have seen at the top, comprising 30 seconds. You do it for one pendulum, do it for the second, do it for the third, and you start drawing your diagram, which is called response spectrum. And this is what our response spectrum will look like. This Sir, how many questions do you have? 2 questions only?
Yes, so far too.
Okay. This is the type of diagram that will lead this exercise you to. This diagram that we have plotted only 3 points. If you continue with the subsequent points, what you get is this. You keep on increasing the period, take pendulums of different time periods, subject them to the same acceleration time history, and on the vertical scale or on you either plot displacement or plus velocity or plot acceleration, because displacement is the first thing. Its dy by dx is velocity, which is the second thing, and again its d2y by dx2 is the acceleration, which is the third thing. On this graph, it is called a tripartite graph. It has velocity on the vertical axis. It has acceleration on the diagonal axis, moving from right below to left top, and it has displacement moving from left bottom rightwards to the top. It has 3 parts. It was observed long time ago that the first part is called acceleration sensitive part. Middle part is called velocity sensitive part, and the right part is called displacement sensitive part. The diagram that you see is normalized diagram. The fact that the values that you have drawn here are not the values that you experience on the ground must let you to understand that there is a difference between the acceleration felt by a particle at the ground and that sitting on the building. So first one is ground acceleration, and what we have drawn here is the spectral acceleration. Spectral acceleration is experienced by a particle that is sitting on a building, having a period equal to t. That is just on the ground. So because of this difference in the periods, we need to draw first, in order to understand a normalized graph in which the scale is so shifted that acceleration on the ground is moved, acceleration on the ground divided by acceleration on the particular floor of the building is 1. Velocity on the ground divided by velocity on the same floor of the building is 1. And the displacement on the ground is divided by displacement on the same floor of the building is 1. The scale 0 is shifted. No other jugglery with the scale. Just 0 is shifted. So you note that the horizontal line touches the velocity line at 1. The acceleration line, which is the left part, touches the acceleration at 1. The displacement line, which is starting from lower part at the bottom, moving upwards to the left, touches the diagonal line at 1. So these three parts are called respectively, as you look from the left, moving on to right, left, acceleration sensitive part of the response spectrum, central, velocity sensitive part of the response spectrum, and right, the displacement sensitive part of the response spectrum. So these are the three parts. And the important thing is the last thing. I will skip everything and I will draw your kind attention just to the last thing, which is the conclusion of what I want to say from on the basis of all this. These are the response spectra for a region, for instance, or a country, for instance. And when I superimpose them, this is a real diagram. When I superimpose them, I get a wide scatter of the diagram. Recently, for instance, Pakistan's code has been made, and as I expect, people should have access to so much record of the past and so much prediction about the future, so that they could construct such response spectra as are reasonably probable, and then see what the mean value is, and then draw a diagram which is either the 84.1th percentile or 50.0th percentile, which means that 50% chances that the diagram will be exceeded, or 84% chances that the diagram would not be exceeded, and the building would become more expensive. What you must understand is that in order to do this, we are not talking about histories of past earthquakes. We are talking about future. We are talking about potential earthquakes from the movement that is taking place potentially at various locations within the Himalayan plate and the Eurasian plate, under the interaction of which the Himalayas are moving by about 2.7 centimeter every year, going up. And a great earthquake every 300 or 400 years apart is always expected from this region. So there is a strain built up in this area. And unless we can predict what will reach at every site in Pakistan, based on frequency content, the type of soil through which it travels, these attenuation functions, and so on, so forth. It will be a tall order, a momentous task for a committee to come up with a consensus, sort of earthquake mapping of the country without having access to the data that is accessible to people who are controlling the recording stations around the world. I have skipped a lot of material because I did not have a lot of time at my access. This is like 5 and 10 minutes. I'll leave them for the questions. Thank you very much for your patience.
Thank you, Rizwan, for such a nice, informative lecture. And I hope that the young engineers must have learned from what you have deliberated today in such detail, and with all the calculations, equations. So I'm pretty sure this would go in the benefit of all young engineers who are in the participants today. Now we have two questions, and kindly please be brief with your questions. One question might need some detailed answer, but please try to curtail it. We have already spent, I think, 1 hour and 50 minutes. So uploading becomes very difficult on our website because of the size of the file. So please, the first question is the shorter one. I'm asking the shorter one, short question first. What is the global coordinate and normal coordinates? Can you just briefly answer this question?
I'm not aware of the terms.
What is the global coordinate and normal coordinates? I think
I'm
they're
not
asking
aware of the terms.
X, Y, Z, and
No,
those
not,
terms.
there could be local coordinates and global coordinates, but not normal coordinates and global. I'm not saying that
Yeah.
is incorrect. I'm saying I'm not aware of the term.
Maybe he's asking the local and global coordinate. If you
Okay,
can,
okay. This is possible. This is possible.
yeah, please answer it very quickly.
Well, you have a local coordinate system and you refer your coordinate system to that locally adopted system. These will be local coordinates. But when you are moving on the basis of global northing and easting based on commonly accepted northing and eastings, it will be global. Wherever you go, you will have the same value. Yes.
Okay. This question was from Mr. Zari Khan on Facebook. And the second question, in fact, it's the first question. It requires maybe a little detailed answer, but try to curtail it as much as possible.
Okay.
Mr. Shafiqur Rahman on Facebook is asking, an arches and column buckling has been discussed. Please guide on buckling stability of large domes, shells, and arches. Also help us with any good reference material on this subject.
I think this is a question which relates to the handbooks that are available. A lot of basic work has been done by Timoshenko of late, and in his famous books on strength of materials and theory of elasticity and similar subjects. He has treated most of the elements under various end conditions. For particular materials, for instance, how to deal with concrete, how to deal with masonry, how to deal with steel. I must strongly recommend for a practical designer that you cannot base it on the theoretical value alone. You should follow your code. The code will place a limit on the K/R value and what will be your F allowable value. Don't follow the fundamental definition provided by one of the books on mechanics. Yes, this is a short and practical and very correct answer.
Well, this you have told them to refer to the handbooks. Would you like to say anything on buckling stability of large domes and shells? A brief note and arches.
There are textbooks on domes and shells which deal with tensile forces in one direction and on the compressive forces at the right angles, and then talk about buckling behavior and buckling limitations. They do.
Okay, thank you. And now we have Hazik Zahir again on the Facebook. He's asking, what if we do not change the time period, but instead changing the mass to evaluate the response spectrum?
You can't do that. The moment you change the mass, the time period will be changed. Because it is K over M under root.
I hope, Zahir, your question is answered, but if there is still you think you need some more answer, I have few minutes. I can wait for you to text it, and then I will read the question. We do not have any question on Zoom, so I think we do not have. Let me check it again.
Zahir, don't take this in terms of M. Just take it in terms of period. You are changing period by whatever means, either by changing M, or by changing K, or by changing both. Just keep on changing time period. This will make it easy for you to understand.
Rizwan, I got his message. Zahir has texted me that, thank you, sir, I got it. So I think he has understood it well. That's nice. So now before I close this session, Rizwan, I will request you to please unshare the screen, please.
Okay. If I can, because I had great difficulty initially.
While you try your effort to unshare the screen, I have to make some announcement, or rather a note, that I today, frankly speaking, I was a bit disappointed and a bit irritated with the attitude of few participants. I will not take their name, but I have been requesting them again and again to switch on their cam. All my efforts in requesting them to switch on their cams went unheeded. So I have to inform you again that this is the requirement of Pakistan Engineering Council. They have given Pakistan Society of Civil Engineers permission to hold this webinar on Zoom software, and we are doing so under their permission. But if they come to know that we are not observing their rules, this permission they can withdraw anytime, and society cannot afford it. So today I am very sorry to inform the 3 participants who remained off air. I would say they did not switch on their cam, and as far as we are concerned, they were off air. So they have been marked absent and they will not get their certificates. I'm really sorry to say, because this is something to do with the permission that we have got with the PEC after long effort, and we cannot afford that PEC should they withdraw this permission. So I'm really sorry to say this thing. And now, thank you again, Rizwan, for such a wonderful lecture. And I would like to especially thank our viewers on Facebook for asking questions and listening to the lecture so carefully. It was really a very technical, highly technical lecture, and very good stuff for the young engineers to, for as far as structure designing is concerned. So now the announcement about the next lecture is going to take place on, that would be this is lecture number 47. That would be lecture number 48. It will be on, it is scheduled on 12th November 2022. The topic is tall buildings, geotechnical aspects, and our guest speaker would be Engineer Sohail Kibriya. Certificates, you people can I will give me a second. I will just switch on. Okay, now I cannot share the screen from my end because if the recording is going on, Zoom does not permit you to share the screen. Anyhow, the certificates you can collect from 19th October, Wednesday. Our address is 148D, Faisal Town Extension, Lahore. 148D, D for daughter. 148D, Faisal Town Extension, Lahore. And there, the person in charge who will give you the certificates is Ahmad Akram. His cell number is 0347 462 5111. I repeat, Ahmed Akram is the person whom you can contact on cell number 0347462511. So thank you very much. We are already now almost 2 hours of this recording. So thank you very much for watching this technical lecture number 47. And inshallah, God bless you all. I will see you on 12th November 2022 with the lecture number 48. Thank you and Assalamu alaikum.